you may know as one of the co-inventors of superconducting qubit architecture. So a very, very foundational person in the field. We're very honored to have him speak with us, and we can't wait to hear from him. So thank you so much for being here. I hope you enjoy his talk, and thank you, Professor Girvin, for agreeing to give it.
Okay, thanks, Brennan. Okay. See a few familiar faces. And hopefully people online can hear through the microphone, which is on Pranet's computer, I guess. So this is kind of a general introduction, gee whiz talk about what's quantum computing, why are people excited, and some of the basic ideas in as non-technical a way as possible. I'm teaching a course in the spring in which this will be the first lecture, Physics 345, on quantum information. For undergraduates, only prerequisite is you have to know complex numbers and you have to be moderately familiar with linear algebra, but you don't need to be a physicist. Okay, so yeah, so there's a second quantum revolution underway, and we're trying to build computers that have seemingly impossible properties, and that's what I'm going to talk about. Assuming we can get this to work. So some vocabulary for beginners or non-physicists. I'm going to talk about classical mechanics. That's the old-fashioned but extremely good theory of the motion of objects through space and time, developed by Galileo and Newton. We use it all the time to land spaceships on the moon, send satellites to Jupiter, and so forth. And it says that objects have well-defined positions. They move along well-defined trajectories that are completely predictable if you know all the forces like gravity that are acting on them. Works perfectly well for large objects like rocks and footballs and planets and so forth. But fails for very small objects. And that is like electrons and atoms and particles of light. And that theory, which does explain that, it is quantum mechanics. It is completely consistent with classical mechanics for large objects, but makes different and correct predictions for small objects at the atomic scale. And it's the most accurate and best tested theory in all of physical science. And in this theory, particles do not have well-defined positions or well-defined trajectories. To calculate the probability that a particle goes through one of these two slits and lands over here, you have to consider the possibility, the properties of the trajectories through both slits as if the particles were waves, and add up the wave amplitudes here, square them to get the probability that you're landing somewhere, and you get interference. Sometimes you have some amplitude to go through here and some amplitude to go through there, and they cancel each other, so you can't end up at that spot. If you close one of the shutters, which you would think would make the light or whatever it is dimmer, it actually makes it brighter at that spot because it shuts off the interference. So the classical picture of an electron orbiting around a proton in please, what is the message that's coming about this? Oh, on the YouTube live. Okay, that's beyond my above my pay grade, and the people who know how to run the computers have left the room. Okay. So in the hydrogen atom, electrons actually undergo sort of planetary orbits under the Coulomb potential, the Coulomb interaction, just like 1/r potential, just like in gravity. But the motion is not a well-defined orbit. It's some fuzzy wave-like thing where you're not quite certain where the particle is. So in some sense, particles don't have well-defined trajectories. They can take all possible trajectories to get to their destination. They act like waves. So with that background, now we'll distinguish classical computers. We have classical mechanics, quantum mechanics. Classical computers are ordinary electrical and mechanical objects that follow the laws of classical mechanics. Quantum computers are completely new things that use objects to hold the information that are quantum mechanical, that obey the laws of quantum mechanics. And so the first theory of the quantum was developed beginning around 1900. The full modern theory was, we're having some problem with the YouTube, or there's a note. There was a thing in the chat. It was too small for me to read. But so the full modern quantum theory was developed. The 100th anniversary will be next June. I'm actually organizing a conference on a small island off the coast of Germany where Werner Heisenberg had the idea in June of 1925. And this theory was a real revolution. It said, it successfully described behavior at small scales. It said particles act like waves, like electrons. Waves act like particles. Light, which everybody thought was made of waves, has particles in it, and there are counterintuitive effects. You can do exactly the same experiment with exactly the same conditions and get a different result, get a random result each time you do it. And there's this other thing, entanglement, or Einstein hated, called spooky action at a distance, which will takes a while to explain. And Einstein, contributed dramatically to all the ideas that led to the invention of the quantum theory. He invented the idea of a particle of light, the photon, and other ideas, but he did not like the fact that the predictions of the theory gave you probabilities that certain things would happen. It wasn't definite what was going to happen. And he hated that, and he said famously, God does not play dice. But the joke is that it was Einstein who gave God the dice in giving all these ideas that led to the quantum theory. And so, the people that invented the quantum theory were, theoretical physicists like me, who were just doing curiosity-driven fundamental research about light, how it is that atoms emit what looks like white light, but when you spread it out into its spectrum, you see different colors here. This is a little experiment I did, taking a compact fluorescent light bulb, shining the light through a slit. There you can see the white light. But if you look off at other angles, you see the light has blue, green, yellow, red components. And those correspond to the quantum jumps that electrons make between quantized orbits. Not all energies are allowed. There are certain discrete energies. And when they jump from one to the other, they emit light of different energies, which corresponds to different color. Well, that was all very exciting and wonderful for fundamental physics, but how could it possibly have any applications? Nobody, could imagine actually gaining enough control of this phenomenon to do something interesting with it. Nevertheless, by the 1950s, there was a huge technological revolution based on the quantum theory, led to the transistor, the laser, and the atomic clock, which on which the global positioning system is based. And the inventors of quantum mechanics didn't foresee these devices, and the more practical people who invented these devices did not foresee their applications. So here's Charlie Towns, 1953, with some big, massive experiment building one of the first atomic clocks. And he and the other inventors of the atomic clock did not foresee the idea that if you put atomic clocks into orbit around the Earth and they all transmitted their time to your phone could not only know what time it is to within a nanosecond, it could know where it is on the Earth to within about 3 meters by having precision time. And this was, completely not anticipated by the inventors of atomic clocks. Similarly, here's the first transistor, 1947. It's about half an inch across. You can see wires soldered onto it, blobs of solder here. It's a hand-assembled device, pretty ugly looking, but it worked. It made the first amplifier to replace vacuum tubes, which you may or may not know what they are. That's what computers used to be built out of. And but these very brilliant people who won the Nobel Prize for this invention did not foresee this device with hundreds of millions and several billions of transistors inside. And they certainly could not predict the rate at which transistors are being produced today. Every second of every day in the world, there's about 20 trillion transistors produced. It's a good thing they're small. Otherwise, we would just run out of stuff. Okay, so we're now at the early stages, very early stages of a second quantum revolution. And what we've come to understand is that these 20th century quantum devices, the transistor, the laser, the atomic clock, you had to know the quantum theory to invent them, to predict what color light comes out of the laser, to predict what voltage it takes to turn the transistor switch on, how fast the atomic clock ticks. You had to know the quantum theory for that. But once you've built it, you can give it to engineers to make it practical, and they don't need to know the quantum theory to make it work. They just know, oh, if I put 0.8 volts on a silicon transistor, it turns on. That's all they have to know. So what we've come to understand is that while these are quantum devices, they do not harness the full power that's available to quantum machines. And this, we've now come to understand this not because we have a successor to the quantum theory. Quantum theory is still working fine. It's just that it's so weird and strange and counterintuitive that we've only recently fully come to understand, well, maybe not even yet fully, but we've come to understand much more about how quantum systems and quantum states can carry information. So yeah, so the new idea is that the really weird features of the quantum theory, that there's uncertainty and randomness and this spooky action at a distance, they're not bugs. Like, they seem like bugs because in the Newtonian theory, I can predict exactly where a particle is. In the quantum theory, I can only give you a probability distribution for where it is. So it seems like you know less. It's like a bug in the program of the universe. But we now realize, actually, these are features that we can use to develop practical and important new technology. So the randomness, for example, that when someone tries to measure something, they can get a random result. That actually can be used to do encrypted communication, secure communication, protected by the laws of physics, unlike, say, the RSA public key encryption algorithm, which is protected by the difficulty of solving a certain math problem. the presumed difficulty of solving a certain math problem. So the second quantum revolution, sort of like a stool with three legs. It has a component, and everything I told you about how people couldn't predict things. That's so I can now, if you ask me any questions about where are we going to be in 10 years, I can just say, I don't know. But we're in the early stages of the technology. And there's quantum materials. There's new things like single atom thick layers of graphite called graphene, and you can put another layer and twist them 1.9 degrees, and suddenly it becomes a superconductor, and a little bit different twist, it becomes a magnet. There's all kinds of crazy things where electrons display quantum mechanical behavior that we can now control that we didn't understand before. There's quantum sensing. Part of the quantum theory, an important part, is measurements and the role of the observer. When you observe something in quantum mechanics, it changes. And we now understand how to make measurements of the tiniest signals at the limit of what's allowed by the Heisenberg uncertainty principle. And this is used in LIGO, the gravitational wave observatory that sees black hole mergers about once a week. There is an experiment at Yale that uses quantum sensing to search for the dark matter in the universe. 80% of the stuff in the universe that causes gravity is some invisible matter, and we have no idea what it is. And the reason you can build quantum sensors is that quantum mechanical systems are exquisitely sensitive to external forces and perturbations, interactions with the environment. That's great for building a sensor. It's terrible for building a quantum computer, because you don't want the answer to be random and perturbed by whatever the environment of the computer is. You want it to just take the input you give it, do a calculation, give you the output. And so we're still in the very early stages of the technology where the pretty big quantum computers exist, thousands of qubits, but they make a lot of errors. And I'll talk about that later in the talk. So we're in what's called the NISQ era, noisy intermediate scale quantum era. Maybe we've invented the quantum abacus or the quantum transistor or vacuum tube, but and rudimentary computers exist, but they're not yet doing economically or scientifically valuable things. It's still very early days in the technology. There's a lot of hype. This famous graph of how hype cycles work. So we're, there's lots of venture capital going into this. Some people are definitely going to lose money, but I think it's safe to say that with additional, decade or decades of fundamental research and engineering scale up, that the quantum machines will cause a technological revolution, perhaps as great as the one in the 20th century. Okay, so quantum computing is not like just a way to build faster computers. It's a completely new way to store and process information. It uses the superposition principle that you can be uncertain where particles are or they act like waves. Your bit, you can be uncertain whether it's 0 or 1. That seems like a really bad idea for a computer if you're uncertain what the information is. But there is a sense, not exactly correct, but there is a sense in which the quantum bit called qubit can be both 0 and 1 at the same time. That's not strictly the right way to say it, but it's a sort of, if I meet you on the street and have to say one sentence, that's sort of the one sentence summary. And entanglement, which involves superpositions of two qubit states. Qubits in different parts of a computer or at different ends of a quantum communication channel can have correlations in their states that are stronger than is possible classically. And so you can do weird things like teleportation of quantum states using this thing that Einstein objected to, spooky action at a distance. And the irony is that, the way we do the engineering test to make sure our quantum computers are quantum and not classical is every morning the graduate students come in and check the thing that Einstein said was impossible. And if the computer's doing it, it's working. Okay. So these weird features of superposition and entanglement give you a kind of massive parallelism that lets the computer complete certain, not all, but certain complex tasks very rapidly. Not because the clock speed is higher, it's actually lower, but because the degree of difficulty of the problem as a function of some size, n, like the size of a database or the number of equations you have to solve, some measure of the size of the problem, you can prove that on a classical computer, it's exponentially expensive as n increases. And on a quantum computer, it's only increases as some power of n, so polynomially. So you might ask, well, what powers do quantum machines have, say quantum computers? They're not a universal solution to all hard computational problems. There are some problems, that are easy on classical computers, like I can multiply large numbers on this computer. But if I say to you, here's a 300-bit number, and I'm telling you there's two prime numbers that I multiplied together to get that 300-bit number, please find those prime factors. That's believed to be exponentially hard on a classical computer, and it's proven mathematically to be very easy on a quantum computer if you can build a large quantum computer that can run for a long time without making any errors. Okay, so this will defeat public key, certain types of public key encryption. And you might think that quantum mechanics reduces privacy, but it turns out using quantum communication, you can enhance privacy and protect the information even against an adversary who has a quantum computer. So in the end, privacy actually wins out. It's an open research problem to classify, whether certain tasks are easy or hard for quantum computers compared to classical. And but I think it's also important to understand that, like in logistics and finance and other optimization problems, people make money every day using classical computers to approximately solve supply chain problems and things like that, which computer scientists know are in principle exponentially hard, or at least there exist instances that are exponentially hard. So, and they use heuristics to do that. And now that quantum computers are becoming available, I'm hoping that young people like you will play with them and figure out some heuristics to solve really hard problems. One interesting thing, computers are a significant source of carbon dioxide production in the Earth's atmosphere, and it's getting much worse now with AI. They're literally starting up nuclear reactors like the one at 3 Mile Island to train neural networks. It's a little crazy. One interesting thing about quantum computers is if they consume any energy, they didn't work. They're like a frictionless machine that can go forward or you could play the movie backwards. That's a perfectly okay algorithm as well. They're completely reversible in their dynamics. There's no friction allowed. Now, it turns out there's a tiny cost to erasing information, to forgetting what the previous calculation was and resetting the bits to 0. That's a small cost for that. And I'm neglecting, like for our computers that I'll tell you about here at Yale, we have to cool them down to 0 with big refrigerators and have piles of classical electronics and classical computers to operate them. So they actually consume quite a bit of energy, at least in this early experimental stage. Okay, so now let's talk about information. And just to remind you that classical information is physical. It's carried and stored and transmitted by physical objects. For example, you can have a battery and a switch that can be on or off, and that can represent 0 and 1 of a qubit. And you can transmit the qubit value by having a light bulb in the circuit. And when the light bulb is on, the switch is closed, the bit is 1, and everybody that sees the light bulb can know the value of the bit. Quantum bits or qubits, they can carry information in a physical system. It could be an atom, a molecule, an ion, a particle of light, a photon. At Yale, we study superconducting circuits that I'll tell you a little bit about. Can be mechanical oscillators. It's any system that has discrete quantized energy levels, just like the electrons in an atom that I showed you with this spectrum. And you label 2 of them, usually the lowest 2, but not always, the lowest 2 energy states, 0 and 1. And those are the 2 states of your qubit. And so I want to first convince you that quantum information is digital or binary. The energy levels of a quantum system are generally discrete. And if you measure the energy of an atom or whatever quantum qubit you have, you'll always get either the energy corresponding to state 0 or the energy corresponding to state 1. 2 possible results. Well, that's just like a classical bit. If you read it out, look at its value, it's either 0 or 1. You never get anything else. On the other hand, quantum states are kind of analog. And the reason is the superposition principle. You can have a state which has some what's called quantum amplitude to be a 0 and some amplitude to be a 1, here represented by arrows, just another way of doing a notation. And so instead of just these 2 states, there's a whole continuum of states, which we can describe geometrically by a sphere called the Bloch sphere. And the state at the North Pole is spin up or 0. The state at the South Pole is spin down or 1. Two different languages, notations for the same thing. But you can have superposition states that are partway in between. Located here represented by an arrow that points to the surface of the sphere. And the direction that arrow points is controlled by 2 angles here, theta and phi, and like latitude and longitude. And the state can be continuous, and the errors in the state can also be continuous. So it's very analog, like analog computers that have gears that rotate continuously. So unlike classical bits, qubit states and errors are continuous, they're analog. And yet, if you measure, are you in 0 or 1? The answer is always that it's in, yes, either 0 or 1. But when this arrow is pointing partway in between, there's randomness. This tells you the probability that you'll get 0 or 1. When the arrow is close to the North Pole, you mostly get 0. When it's close to the South Pole, you mostly get 1. So this is the superposition principle. It's very strange that an arrow pointing to the right on the block sphere is a superposition of the arrow pointing up and down. And sort of you're in both states at once. So sort of you can give the computer all the possible inputs that you could ever give it, and it can calculate on every input value in parallel. That's a little misleading, but that's sort of that's the simplest way to see where some of the speed up comes from. I'll try to improve the picture shortly. So a classical register of n bits can be in 2 to the n different states, representing binary numbers from, let's say, here's 3 bits from 000 to 111. 2 to the 3 is 8. There are 8 states, 0 through 7. But a quantum register can be in a giant superposition of all 8 states at once, and the coefficients, the quantum amplitudes that go in front of here, which aren't exactly probabilities, but if you take their square, you get a probability of seeing this. It can be a complex number, but for simplicity, I'll just say it can be plus or minus. So I have 2 to the n choices of plus and minus signs, giving me a total number of choices of 2 to the 2 to the n, which is a huge number. So even a small quantum computer with, say, 53 qubits has 2 to the 53 possible states, not even counting all these superpositions, just basis states. And that's about a petabyte of classical storage to represent all of that. And so if you want to simulate what a quantum computer does, or you don't have a quantum computer, so you have to do the calculation on a classical computer, it's very difficult to work with a petabyte of storage and do calculations. Okay. So we're uncertain, right? If I take a bit, which is represented by an arrow on the block sphere that's horizontal, neither up nor down, a superposition, we're uncertain when I make a measurement of it, what the outcome is going to be. If I make the measurement and I discover, oh, it's pointing, I'm asking the question, what's the Z question? Are you pointing up or down? The answer is yes. It's always either down or up, but I can only predict the probability of each result. I can't predict what's going to happen the next time I do the experiment, even though the conditions are exactly the same each time. There's an ineluctable randomness. And the act of measuring actually changed the state. It was like this. After you measure it, it's like this or like that. It has changed. And there's no way for you to know that this back action, this effective measuring happened. You just see, oh, I measured it and it was up, or oh, I measured it and it was down. Completely random result, but you don't know that it changed. It could have been, if it had been up and I sent it through the apparatus, it would come out up. If it was down, it would come out down. So if I measure it again, I will get the same result as the first time. The first measurement is random, all the rest are the same. But this back action that changes the state when you observe it is invisible to the observer. That's going to turn out to be scary when we try to figure out how to fix errors, because we have to make a measurement to see if there's an error. So my friend Sasha Karakov likes to say, in quantum mechanics, you don't see what you get what you see. Meaning, if I have a box and there's a qubit in there, and I open it up and I see each time I do it, I get a random result. Classically, I would say, oh, there's something in the box. It's definitely in the state, some state. I just don't know what it is. I can't calculate it because there's some, I don't have all the information I need. But the universe knows what it is. Well, it's not true. I mean, I just open the box and see what state it was in. The act of opening the box and looking at it creates the state that you see. The act of looking creates a state. And before you looked, this state, which is horizontal on the black sphere, is neither 0 nor 1. It doesn't have a value until you measure it. Okay, so if I can put one of these giant exponentially large superpositions, which are easy to make, by the way, of all possible 2 to the n states into my quantum computer, I give it all the inputs I could ever give it. And in fact, the answer is in there. If the output register is the same size, one of these is the answer that I'm looking for. But if I just measure this state, it randomly collapses by this back action effect to either this or this or this or this. And then one of these is the right answer, but it's exponentially unlikely that I get lucky and it's the one that it collapses to. Okay. So that's a problem. Actually, making measurements that are perfectly random numbers are extremely useful in computer science and in cryptography. When you call a random number generator on a computer, it's not really random. It's just some crazy function that is chaotic and hard to predict. But these numbers that you would get out of here are truly random. Okay, so how, you've raised your hand. How can quantum algorithms produce useful results instead of just this random state collapse giving you a random result? Well, we're going to use the wave-like nature of particles. It's hard to explain what the wave-like nature of qubits is, but it has to do with the fact that they can kind of rotate around on this block sphere. And wave interference, you probably know, if I have 2 waves, like water waves or sound waves or light waves, and they're in phase and I add them, I get a more intense wave. And the greater intensity, the more likely there are particles of light in that part of space. That's constructive interference. And if I add them together when they're out of phase, they just cancel. And I talked about that in the 2-slit experiment. So what I want to do is most quantum algorithms begin by just making this giant superposition of all possible input states. And then the program or the algorithm has to apply wave-like interference to kill off the quantum amplitudes of the wrong answers and enhance with constructive interference the right answers, so that when you make the measurement, you have a much higher probability of getting the right answer than the wrong answer. Okay? And you'll get the right answer with high probability. And if you run it 3 or 4 times, you'll find the most probable thing and be able to see that it's right. So you can kind of think of this as a programmable diffraction grating, like that thing I showed you that spread the white light out into the different colors. So you can imagine I have some waves emanating from the input, and they're going to spread out and put output everywhere, but I'm going to block certain trajectories so that there's I keep only the ones that will constructively interfere at the location of the right answer in the output. And then I'll have a high intensity there, and when I look, I'll see the light or whatever it is, the qubits, focused on this place. That's roughly how quantum algorithms work. But then, how do you actually do that? How do you invent a new algorithm? If you're trying to solve a problem and you don't know the answer, how do you program the diffraction grating so that it gets constructive interference on the unknown right answer and destructive interference on all the wrong answers? Well, that's the grand challenge and why it's not completely easy to invent quantum algorithms. Okay, so the quantum hardware, there's all kinds of things: trapped ions, cold atoms held by laser beams in place. I'm gonna talk about superconducting electronic circuits. That's what we do here at Yale. Where we is my experimental colleagues. I'm a theorist, and right now, quantum computers, even IBM and Google and Amazon and Intel, they're all hand-assembled devices. They're not mass-produced. This is a picture from work at Yale in Beckton Laboratory. And the very first all-electronic quantum computer that didn't use, lasers and individual atoms was developed here at Yale in 2009 in Rob Shulkoff's group. It had 2 quantum bits and could run some very small algorithms on these 2 quantum bits. And this idea that we developed, this so-called circuit QED, where you have qubits that act like artificial atoms coupled to microwave photons, is now the basis of all the superconducting qubits that are made at Google and IBM and Rigetti and Intel and Amazon and Northrop Grumman and there's a startup here in New Haven as well. And these are all Yale alumni. So the artificial atom that makes up our qubit is huge. It's a millimeter in size. Young people can see it without a magnifying glass. I need a magnifying glass. And it's like a little antenna, like a little radio antenna with 2 halves separated by a gadget called a Josephson tunnel junction. It's 2 pieces of aluminum this is about 2,000 atoms on a side, very small. And in between the 2 layers of aluminum, there's an oxide that's a barrier that the electrons should not be able to go through, but because they're quantum particles and they're waves, they can actually tunnel through this barrier in pairs. And when you cool this down near absolute zero, the aluminum becomes superconducting. It flows without any friction or dissipation. And the excitations of this atom are pairs of electrons sloshing back and forth in this antenna. Just like in a radio transmitter, when you apply a voltage and send current back and forth in the antenna, it radiates photons, radio waves. So that's why we build it like this. And this artificial atom, when it's in an excited state, can spontaneously decay and emit a photon, just like the these are not fluorescent lights, but the way light bulbs work. And but here they emit microwave light, not visible light. So it's 100,000 times lower in frequency, about 5 gigahertz, 1 billion hertz, around the same frequency that your cell phone works at. So we have to shield them from all the cell phone radiation that's around. And why do we have to cool these things to near absolute zero? Well, the superconductivity, the zero resistance current flow only takes place below about 1 Kelvin, 1 degree above absolute zero. And so the other thing that's important is the excitation energy of the atom corresponds to a frequency of 5 gigahertz, as I said. And 21 gigahertz corresponds to the energy that you have typically in a system that's at a temperature of about 1 Kelvin. So the excitation energy of these atoms is 1/4 of a Kelvin. And so if you kept them even at 4 Kelvin, the temperature of liquid helium, they would be bathed in a bath of black body radiation, like heat, that would make them jump from ground state to excited state and back. So we have to cool them to 1/100th of a degree above absolute zero, 10 millikelvin. And so we're dealing not with visible light like in atoms, but microwave light with these artificial atoms. And instead of using a household refrigerator, we have to use a $750,000 fancy refrigerator that cools down to 100th of a degree above absolute zero. That space that the computer's in is the coldest place in the universe. The outer space has a temperature left over from the Big Bang of 2.7 Kelvin. The microwave background is full of photons. This is 300 times colder than outer space. And the electronics that goes with this are also very expensive. Fortunately, because the frequency is about the same as your cell phone, there's a lot of commercial electronics that, while very expensive, is available. If it were higher frequencies, it's just very difficult to work with. So the huge information content that I said of quantum superpositions comes with a price: great sensitivity to noise and perturbations and dissipation. And I told you that the states are kind of analog and the errors are analog. You can just rotate the arrow on the Bloch sphere a tiny amount. That's an error. And that's bad, actually, because we know from the 1950s when people built analog computers, either with gears that were turning or voltages that could vary continuously, that it's impossible. This is someone programming an analog computer by plugging wires together. Just completely crazy. We know there's a no-go theorem that analog computers, if they make errors, you can't correct them because, if the position of a gear is a real number, and any real number is an allowed state of the gear. So if it's erroneous, you have no way of knowing. So that seems like we can't correct errors in quantum systems. There's another problem, which is that, and here's the problem in a nutshell. I'm going to give you an unknown quantum state. If you were to make a measurement to see if it has an error, it would change randomly due to this state collapse, the back action. And your job is, if it develops an error, please fix it. And that's another thing that seems impossible. But miraculously, it can be done. In principle, it's been proven, and now it's finally been done here at Yale for the first time in practice. And the trick is that you can add some extra qubits into your computer and have them change state to a new state if there's an error. They may rotate a little bit because there's a small error. But then when you measure that extra qubit, you either get it was 0, meaning there's no error, or it was 1, meaning there's a discrete error, and you know exactly what the error is. It's not continuous anymore, and you can fix it. So that's how you get around this loophole that there's no error correction for analog systems. Errors are continuous, but measured errors are discrete. And you have to do this very, very quickly because errors happen rather rapidly. And there's some very high-speed electrical engineering and computer science stuff that has to happen using what are called FPGA cards. And they have to perform the measurements, make a decision about what to do based on the results of the measurements, and send signals back down to the computer to correct those errors. And it has to do all of that in 200 nanoseconds. 200 times 10 to the minus 9 seconds. The speed of light is 1 foot per nanosecond. So 15% of this latency time is just the time it takes the signals to travel in the wires at the speed of light from the computer down to the quantum computer and back. So this thing has to be very, very, very fast. And this was first successfully done here at Yale in Rob Shulkoff's lab. So there are all kinds of challenges for young people in this field all across the stack, from the bottom, where we have to find good materials to build qubits. We have to build cleverly arranged devices. We need applications, software, error correction, all kinds of things where we need all kinds of people to help people, material scientists, computer scientists and engineers, chemists, physicists, and there's just huge number. It's a very, very interdisciplinary field. So, okay, you're now all experts, so we better have a quiz. I know you're really doubly expert because you already, Harsh gave a lecture earlier, I guess. So, is quantum information carried by waves or particles? Yes. Is quantum information analog or digital? Yes. Okay, you're catching on. So I hope I've explained to you that quantum information is carried by waves and particles, and they're sort of the same thing. It's both analog and digital. Quantum error correction is possible. It's still very, very difficult. We're only beginning to be able to do it. It's the frontier area of research right now. And the hardware, very important. There's a lot of hype. So I just want to say hardware is still in a very crude stage, like this first transistor. We have a long way to go, but we're making very rapid progress. And the second quantum revolution is coming about because new understanding of quantum weirdness is that it's a feature and not a bug. Thank you. Happy to take questions. Yes. If I don't think they're on my webpage, so if you send me an email, I'll happy to send you the slides.
Oh, let me just try to keep it.
Yeah.
It's required you're using qubits that can have more than just 2.
Yeah. So I'll repeat the question for Zoom. Is there any benefit to making quantum objects like qubits, except they have more than 2 states? Yes. So we have a recent experiment in Beckton that made Q trits, 3 levels, Q quarts, which have 4 levels. We haven't tried Q quints, I guess. But if you had a Q quart that has 4 states, that's as many states as 2 qubits, but it's in one object. So you can gain, a factor of 2 in the number of objects. It also turns out that if you have enough control, be able to move around among those 4 states, better than if you had to do it by making 4 states with 2 objects, you get some control advantage as well. So it's not like massive advantage, but right now we're scrambling for every little tiny advantage we can find. So indeed, this is a topic of current research. Somebody back here, yeah.
So when you describe qubit states as sort of parallel computing,
Yeah.
is there an inherent advantage to using them over just multiple classical computers and distributing the computing among those CPUs?
Good. So the question was, I talked about quantum parallelism, qubits being in many states at once. Is there some advantage to that over just having parallel computations and by having many classical cores or processors or whatever? Yes, because the 2 reasons. One is classical computers can't do this interference thing, so we have completely new ways of doing algorithms. But let me remind you that if I have 1,000 qubits, then the number of states that can be in is 2 to the 1,000, which is extremely large. Like 2 to the 10 is 1,000. 2 to the 30 is 1 billion. So it's 1 billion to the 30th power, very big. So you would have to buy a lot of hardware to do as many things in parallel. So that's in some cases, quantum algorithms have exponential advantage in either space or time. That space meaning memory size, you just that is so large that you could never build a classical computer doing parallel computation that could match it. If we can build such a quantum computer, we haven't yet. Sure.
So wondering, like, what are the different types of like errors, and are there certain like quantum hardwares that tackle those errors better than others?
Yeah. So the question is, what kinds of errors are there? And are there certain types of hardware that have fewer errors or different types of errors and that might be easier to work with? So, so I showed you these quantum superpositions, like an arrow pointing to the right is up plus down. If it points to the left, it's up minus down. So you can have what's called a phase flip, where the plus in the superposition becomes a minus. And that means that you move from one side of the Bloch sphere to the other around the equator. You could also have a bit flip error where what was 0 becomes 1 and 1 becomes 0. You have that in classical computers all the time when roughly once every few days, a cosmic ray flips some of the bits in your memory. But there's classical error correction to take care of that. So there's more kinds of errors in quantum. There's no such thing as a phase flip in a superposition in a classical computer. So it has more kinds of errors. So you can have phase flip or bit flip or both, which is another kind of error. Now, some qubits, if you're lucky, the rate of bit flips will be much smaller than the rate of phase flips, let's say. So then it's easier to correct. It becomes more like a classical system, but with only one kind of error. And we've been sort of specializing here in the research group at Yale on trying to invent funny types of quantum systems to use as qubits that have that property, because the errors are easier to correct.
I have a question about the slides where you have the classical easy, quantum easy, and quantum hard.
Yeah.
Can you talk a little bit more about, so are these things that people are thinking about right now, or have they already adopted?
Well, certain things are known. It's known that factoring large numbers is quantum easy. It's only believed that it's hard. The best published algorithm is exponentially hard for a classical system. It's known that certain problems in there exist problems in logistics with optimization problems with many constraints. It's known that there are instances which are hard on both classical computers and quantum computers, but most real-world optimization problems have some structure, and computer scientists are only good at telling us about the worst-case scenario, not the average difficulty. And so we don't know. The average difficulty may be much lower for a quantum computer than a classical computer? We don't know yet. That's an open area of research. So some things have been proven mathematically, other things are guessed at, and other things are still unknown. So it's an area of active research in quantum computer science. Yeah.
How many qubits would you need to, do complicated algorithms, and then how many qubits are in like modern quantum computers or quantum computers right now?
All right. So how many qubits do you need to do something interesting, and how many are there in current computers? So so at Yale we work on small systems with a few qubits, trying to develop new error correction techniques and longer lived, fewer error qubits and things like that, fundamental research. Then industry is spending billions of dollars to scale up to larger sizes. So IBM has a computer with one, or maybe there are more than 1,000 qubits. I've lost track of the current record. Google has some with sort of hundreds of qubits. I showed you that 53 qubits was sort of already pretty big. So it turns out you don't need huge numbers of qubits to do interesting things, but you need them to not make errors, and so that you can run very deep, long-running programs that do complicated calculations. And that's what's limiting us right now. It's not so much the number of qubits. If we were able to make them have fewer errors, it's then much easier to correct those errors. You can build what are called logical qubits out of many physical qubits. And if the individual physical parts are really, really good, the whole thing becomes fantastically good. And it doesn't take you, you don't need to use millions of physical qubits to make one bit that's good. And that's very impractical. So we have to get the errors smaller. And once that works, getting more qubits is not so difficult. I mean, it's a big engineering problem, but it's not a showstopper. Yeah.
I see is with quantum computers, even against like another quantum computer.
Yeah.
Is that fundamental to how the computers work, or is there some like future in which that will not hold?
Okay, so good. So the question was, I mentioned that quantum communication, let's say, lets you enhance your privacy and even against an adversary with a quantum computer. And is that like just true today, or is there could we imagine some way around that with future technology? And the proof of the security is based on the laws of quantum mechanics, which is the best tested and most accurate theory in all of physical science. So it would be extremely unexpected that this situation will ever change. Of course, Newton and Galileo, when they got very excited, they could predict the orbits of the planets. They thought, well, we're all done, but they missed out on the quantum theory. But people have actually very actively studied, could there be something beyond the quantum theory that's consistent with the quantum theory in the regions in the domains where it works? And it turns out the logical structure and the mathematical structure is very, very difficult to change. You get immediately to paradoxes that are inconsistent with observation. So nobody has thought of a way to change quantum mechanics. So, I mean, if we built large quantum computers and they didn't work because the quantum theory was slightly wrong, that would be a fantastically amazing, wonderful result. That would be a third revolution, but we're not expecting it. In the back.
Algorithms you can use different stochastics. Is it possible that
You can so also that is exactly the one state level. So you can ask students.
Great. So I mentioned that the question is, I mentioned that quantum algorithms use interference to kill off the probability of wrong answers and enhance the probability of right answers. Is there a possibility to make the right answer come up with 100% probability? And the answer is, in special cases, yes. But for many algorithms, it just you can make the probability higher and higher, but never make it 1. So for example, Shor's factoring algorithm, when you run it, it produces the prime factors correctly with high probability, let's say above 3/4. You can make it higher and higher by using more and more qubits and being more and more perfect in the algorithm. But once it's above 3/4, you know, you could run it 100 times, and because you can check the answer, right? It's easy to check the answer. So you just keep running it, and you're getting numbers, and you try them and see if they're the answer. And if you do it 100 times, the probability of failure is 3/4 to the 100, which is basically 0. It's e to the minus 25, roughly. So, but there are special cases where it happens that you get exactly the right answer. But it's not generically true.
This idea of creating a logical qubit out of many physical qubits.
Yeah. Yeah.
So is scaling up just more and more qubits a viable way of like functional quantum computers that can do things without errors?
Yeah, that's the challenge. We know that if we use many physical qubits to make a logical qubit, imagine, for example, I have classical bits, and I have, I have 5 of them, and I just look at them and I take the majority vote. Whichever, if it's zeros are more common, I assume it was just it's a 0, and if the ones are more prevalent, I assume it's supposed to be a 1. That's the maximum likelihood interpretation, because it's the minimum number of, you assume the minimum number of errors occurred. But it's more complicated than that for the quantum case. But that's roughly how using more physical qubits helps you beat down the errors. The problem is that if the errors are already are not small enough, like if I take 100 qubits, each of which is having errors with a certain probability, now the probability that there's an error is 100 times bigger, right? Or the errors are happening 100 times faster. So my error correction scheme has to be so fast and so accurate, it has to overcome that factor of 100 just to get back to what you would have had with 1 qubit. And then you have to make it even better than that, so that the lifetime is long. You're not just breaking even, but the lifetime is actually longer. So, and there's another problem, that the circuit, the algorithm you carry out to correct the errors, it also uses other qubits, and they have errors. So the error checking circuit makes errors. And so designing one that still works is called designing a fault tolerant system. It can correct errors even when the error correction circuit makes errors. And that requires the rate of physical errors in the individual parts to be even lower. But once you get below that level, then adding more and more physical qubits makes it better and better and better. And the error rate goes down actually doubly exponentially with size. And So we're just entering the era now where we can make a collection of objects have a lower error than the best of the individual objects. And right now, Yale holds the current world record for doing that. It's a factor of 2.3 better. It's not 10 billion times better, which is what we want. But to get to 10 billion, you have to get above 1. So we're on the way. Okay, one more question.
For the quantum communication you were talking about, would you be able would you be able to use like traditional communication lines between computers, or do you need like some special?
Oh, yeah, good question. So you can use transmission of visible or infrared photons through the air from the ground to satellites, because the air is not that thick. Or you can use optical fiber, which is how traditional communication is done. But quantum information is very sensitive. So one way to store the information is to have the polarization of the light. The electric field is either this way or that way of the photons. And when you send it through fiber, the polarization kind of wanders around like this. That's okay. But every time a truck drives over the street where the fiber's buried, it shakes the fiber a little bit and the polarization changes. So you have to spend almost all your time talking back and forth, correcting for that. But it does work. And people have transmitted light, the quantum signals through optical fibers over some distances, 100 kilometers. Optical fibers are the most transparent thing in the world that's not vacuum. Amazing technology, but it's still, if it absorbs even one photon during the journey, you've lost very important information. Whereas classically, you can just send like a laser pulse with 100 million photons, and if you lose half of them, there's still a laser pulse there that's pretty big, and it's not a big deal. But you can't do that quantum mechanically. So now you have to send a whole bunch of photons entangled in some quantum error correction code designed so that if you lose some of the photons, you can still reconstruct what the state was. And that's another area of exciting research. There's actually a project in electrical engineering. There are undergraduates actually working on it. We're going to make let's see, where are we? Klein Tower is over there, I guess. From the roof of Klein Tower, there's going to be a link to Brookhaven National Lab and Stony Brook University with a telescope going through the air over the sound. And probably it's only going to work at night and only on calm days when there's, the air is not causing the laser to jiggle around. But that's, that'll be an exciting experiment if we can get that to work. Okay, well, thanks for all your questions.
Thank you so much, Professor Girvin. I do want to draw you guys' attentions to quantum.yale.edu, which is like the one website where everything quantum is. So you can just take a look, scroll through, and it contains basically all the research labs and all of the active work going on. Cool. So we will get started shortly on setting you guys up for the hackathon tomorrow, which is super exciting. I will make sure that it doesn't run over 6:15-ish so that you guys.
Get out of your way.
So
Yeah, pleasure.